Hello everyone, we are Antonio and Alberto. We are here to talk about the origin, the evolution and the future of KRule, which is a cloud-native platform for fast and flexible development of cloud-native application through a rules-driven event processing engine. Here the main point we're gonna touch today, the main point we're going to touch today in the presentation. What KRule aims to be and who we are, a little bit of history. The origin of the framework, everything can start as a programming paradigm. Its evolution as a reactive and event-driven framework. Its transition in the public cloud, structuring the framework on a platform as a service. And finally, the transformation and its future as a cloud-native platform. So, who we are and what is KRule? KRule today aims to be a framework that enables fast cloud-native development of real-time and reactive application to an event-driven rules engine approach. The references that have inspired our work are different and composed and are mainly the event-driven architecture and the publisher-subscriber design, the reactive paradigm that was well represented by the reactive manifesto, a rule-based paradigm structured on the event condition action design, the idea of context-aware application, a microservice architecture today, and a cloud-native strategy for our present and future. So, basically, KRule will enable to deploy useful real-time services through event, context and rules. This solution can react intelligently upon changes in the context, performing and automating action relevant to the user, to the application itself, to the business, or to IoT devices. KRule will allow to create, connect and extend application intuitively and fast, basically. Moreover, KRule aims to allow the reuse, the easy reuse of assets that we develop project by project. Okay, KRule can be used effectively for building every real-time data application on a Kubernetes cluster. Example of use case could be use case where we need to manage a large number of devices and large amount of real-time data. For example, in smart city, in supply chain or IoT application. Use case where we need to manage critical real-time events, complex workflow and automation. For example, in smart mobility or smart factory or even marketing or finance. And use case where we need to manage system integration, complex system integration. For example, where we have to integrate legacy software with mobile apps, edge computing, third-party software as a service, and so on. We have been working, who we are actually, we have been working since 2010 as a software house with strong experience in server-side logic and server-side application. And we had a business model based on deliver turnkey project to our customer. So Byters conceived the rules engine as an internal tool in the beginning, just for project delivery. Our objective were reducing solution delivery time, ensure scalability, reliability and elasticity of our application, minimizing the effort for operation and infrastructure management, because actually our company had a strong focus on the application level, but we had not all the competence for the operation itself. So in 2019, basically in the beginning of this year, we decided to focus on the engine itself, transforming this framework from an internal tool to a platform. To do so, we decided to lead the transformation toward the cloud-native architecture and to lead this change that implied a new technology and a new business model actually, and to lead also the R&D connected to this change. We founded a new company. Airspot is the name of the new company we just found. HelpSpot will focus on cloud native development of KRule, and KRule will go open source in our plan in the first quarter of 2020, and based on this open source project, we want to build up a low-code platform for fast solution building in the third quarter of 2020. So, as I told you previously, the origin of KRule arrived from building or envisioning a programming paradigm. In 2013, we had to work for a telco distributor or an app for managing telephone credit top-ups. We needed to ensure real-time propagation of changes on asynchronous events arriving from different emitters. The solution we conceived was a reactive application where data flow emitted by one component had to propagate those changes to all the other components registered to receive those changes. So in 2014, reactive applications were actually at early stage. And we took inspiration from the reactive manifesto, but we ended up learning reactive programming the hard way, basically figuring it out while building with it. We started working on a very basic event-driven architecture and on event condition action paradigm using in-memory data store. The most important component we used at that time were Django as a Python framework, Redis for the in-memory data store, of course, and RabbitMQ like message broker. In that case, the case of credit top-ups, we had to deal with typical click events that generate asynchronous server-side reaction. The stream was a sequence of ongoing events, and each stream could emit three different things: error, a completed transaction, and the value of the transaction. We had to capture this event by defining a function that would be executed for each of them. With this project, actually, we had quite a fair amount of difficulties, including overrun of bug fix and code refactoring, low software maintenance productivity, expensive new feature development, scarce component reusability for other projects, and complexity in collaboration with external developers. So we came out with a good level of stress, but actually we understood that we were not alone with this kind of problem. Most of IT projects actually they have a problem in overrun and bug fix, as I told you before, and the 45% they go on cost overrun, basically. The 56% have a shortfall in value, and only the 60% of effort is spent on new feature development. So this kind of problems are even bigger if compared with the need of business operating today, where product strategy and marketing strategy are faster than IT project development in average. So, we arrive in the evolution toward an event-driven framework. In 2016, we started working on a retail app for managing interaction with customers in a gamified environment, designed to involve people with the brand. So we needed that the app could offer real-time responsiveness on user interaction, and basically we had to deal with an abundance of real-time events that enable a highly interactive experience to the user. We needed tools for properly dealing with that, and we have experience in 2014 reactive application. The benefit of that architecture were evident for us. User interaction had to automatically trigger reaction on user interface and save data to the backend in real time for every connected user. So we decided working on an event-driven architecture based on a publisher-subscriber design. We decided to be a framework based on this project that could become actually an internal tool for supporting the development even on other projects. The programming paradigm we used was inspired by the structure of a context-aware rules engine based on the event condition action. We decided this because the marketing policy we had to activate were easily formalizable in the form of rules. We had to be able to react to event with multiple dynamic logic. And the policy with which the interaction in real time had to be driven have to be easily editable, and we had to be able to easily add new policy. At that time, most rule engines available were conceived as decision services and used in a stateless transaction. The idea of rules-driven event processing was instead processing multiple event streams and sources over time, which require actually a stateful rule service. So we started thinking to overcome the limitation of standard rule-based system by inserting reactive event processing in a data stream managed by a rule-based system with its contextual knowledge. Rather than sharing the knowledge in the ontology or plain code, the knowledge could be easily described in the form of rules that were actually data structure. Adopting a reactive event-driven architecture, actually we went further the if-then-else paradigm, because in a publish-subscriber and declarative programming paradigm, the publisher basically declares a condition and subscriber in a logic of event condition action eventually act. So we had to work asynchronously. The simple reason was that we want to improve the user experience. We wanted to make our application more responsive as possible. And we wanted to deliver a smooth user experience to user without freezing the session, producing the events or slowing them down. We also wanted to do the heavy work on the server, decoupling the client side and the server side as much as possible. At that time, the most important component we used were again the Django framework and Redis, and Celery and Postgres as database. The framework main logic component we conceived were the messages produced externally from user of device or internally by the rules themselves and directed to other set of subscribing rules. The subject store, that was the system reactive component. It was based on Redis, and it groups the logic entities and property recipient of messages and coordinate the concurrent access of messages to the recipient. And then the rules, that are data structure written in Python, representing a pipeline of functions that enable the domain logic. So the messages represent both the rule input and output, of course. Its message was composed from a topic, because at that time the topic was itself part of the message. Now it doesn't work this way. And the message name actually determines the type of action and event and identifies the bounded logic and the expected content, so the payload type. The subject, that was the logic entity representing the recipient and was managed by the subject store, and the payload, that basically was the data structure contextual to the message. Rules, finally, are data structure written in Python that define minimal blocks of logic able to respond to specific topics. Each rule is composed of two sections that are the filtering section, basically the condition, and the processing section, basically the action. Each section is a pipeline of function, and based on the received payload, the filter section establishes if the processing section has to be executed or not, so basically if the rule is activated or not. The subject store, it's the component containing the entities for which the logic is delivered. It represents the context, finally. It can be the context or even the digital twin if we are talking about IoT device. Each subject has specific property, and property may be defined as reactive, meaning dispatching or not messages when altered. The subject manage basically the concurrency in the framework, because multiple processes may concurrently access the same property, and the reactivity, because when a property is modified, a new message can be generated, allowing the system to react. So, we're thinking to have done a good job, but as we can see from the reactive manifesto, a good reactive application needs to be responsive, resilient, and message-driven, and actually we were, but also elastic. And we were not enough elastic to stay reactive and responsive under varying workload, especially in case of peak load. So this situation put us on the way of public cloud and platform as a service. In 2018, we decided to move our Rules engine on a path. We needed a new approach for achieving an elastic reactive system able to stay responsive under varying workload. This implied the ability to shard or replicate component and distribute input among them. The real advantage was in the dynamic allocation of resources for us. On platform as a service, we were loosely coupled with the infrastructure, of course, and so that the app could scale up and down on demand and embrace the idea for us of working with an infinite infrastructure, like we had a very high abundance of resources, of course. Moreover, previously we spent quite a significant portion of our time and effort managing the infrastructure, and now we could concentrate all the effort on the application, gaining, in our perspective, a competitive advantage. So, have we found now our solution? Not really, actually, because we achieved the dramatic benefit in terms of elasticity and scalability, but the application gets locked to the chosen platform as a service. So we started the transition toward the Cloudnative architecture. At the end of 2018, we started a deep reflection about our Rules engine, its value, and its possible future. We identified an interesting business case for a cloud-native KRule. To remain competitive today, enterprises need to continually innovate and add a new feature. They need architecture that are extensible and robust enough to support change. By 2020, Gartner tells us that 75% of applications supporting a digital business are expected to be built rather than purchased. And that is due in part to the cloud-native architecture that is reducing the barriers to entry for development at scale. Organizations must become real-time, and to become real-time they must be event-driven. Especially as more and more devices are connected to the internet, the architecture of cloud-native computer, we think, will become the underlying standard of enabled service system. In cloud-based services, one area that is gaining momentum is in providing services for knowledge representation, and rules are very good at that. And finally, we think that eventing is crucial in a cloud-native perspective. Actually, we had experience in the previous year how event-driven rule-based system could reduce the complexity of developing and supporting real-time reactive application, making the whole process more uniform. Moreover, we identified a simple way to embrace a rich knowledge bases that reflect aspects of the real world. The modern web and the IoT is characterized by a definitive heterogeneous environment, and different type of client and device things, we could say, contribute diverse type of data that are expected to be processed in a uniform manner. The concept of rule itself, we think, is very good for formalizing logic, and it's very flexible to use context and rule for managing events. In fact, if we think, much of human problem solving and cognition can be modeled like rule in the context. However, traditional rules engines show a lack of proper modularization. when they have to deal with a heterogeneous setting of data sources and multi-tenant application. They are characterized by a flat design space where activation could be observed from all data without discriminating the different sources. At this point in 2019, we decided working on KRule itself, not as a tool, but as a business object. We founded Airsport with the mission of making KRule a tool for building cloud-native application using a rules-driven, complex event processing approach. So Airsport is leading this transition and the development toward the cloud-native platform. KRule is based on Kubernetes infrastructure and it is integrating Knative for serverless. We will address we will address developer as target for our platform because the objective of the platform itself is the fast application building. Actually, what changed in the cloud-native transition? First of all, each rule made up of microasset or group of specific rules or rule set are packed into container that act like microservice. Each instance subscribes a topic with any broker. Containers are dynamically orchestrated with Kubernetes, and it will be possible to run KRule on-premise on Kubernetes or on Kubernetes managed. At the main logic component we talked before, we had the concept of source. Actually, source intercept and ingest event from the outside world into the system. They can be the interface to traditional message broker like Kafka, NATS, or PubSub or whatever, or even abstraction on a heterogeneous system where it's possible to identify direct or infrared event. Actually, we are focusing in adopting a fully cloud-native approach to eventing, using the inter- and inter-service communication to standard event definition, the cloud event. We start the integration on Knative and Knative eventing in deeply that provide us the primitive to enable late binding event sources and event consumer. In our vision of sources, each source that produces an event can become a Knative source by encapsulating the information identified as an event in a cloud event standard, making easy to react to this event through rules. Potentially, even an FTP share on which content is loaded can become a source event. Kubernetes itself natively produces cloud event. KRule itself can also become an event source, allowing the definition of rules that listen and react to the process of other rules. Here you can see a very basic diagram of the architecture with a source of Knative, and here you can see another diagram that makes the difference between event producer and source. Actually, the source itself can become event producer and so on.